And welcome to the Crash Training Podcast. We're going to help you work to restore or preserve the highly perishable skill set of crash reconstruction. And welcome everybody to episode number 8, 30DF versus 2AD, back that staying up. Alright, so we're going to pretend that we're dealing with a Mustang in this example just so that creative title works, but we're going to look at how we can use both of these formulas to back a vehicle up from their known ending velocity in this case, but from their known velocity and back them up to the start of the event to see what the speed is. We're also going to be able to do like an apples to apples comparison between these two methods, because a question that we had come through on the podcast was, how is the velocity formula in comparison or with the minimum speed or combined speed, because we have one coming from kinetic energy, we have one coming from a kinematic equation of motion. So let's look at these two and see exactly what kind of results we would get with the same data, same inputs, same variables, and everything else. So before we start, the velocity equation that most of us are used to dealing with looks a little bit different than what I'm just about to put up here, but it comes from one of the kinematic equations for motion, which says that the velocity final squared is equal to the velocity initial squared plus 2 times a times d. And in a lot of physics textbooks, you see d written out as delta x. And that is just showing a change in position. And in our case with crash reconstruction, the change in position that we're going to be dealing with is going to be the distance that that vehicle moved, prior to the event. So you may see it as 2a delta x in some writings, but it's going to be the same thing as saying 2 times a times distance. So if I want to put this in the same usable form of the velocity formula that we're used to dealing with, first, I'm just going to say that velocity final is equal to the square root of velocity initial squared plus 2 times a times d. Because if I want to isolate this velocity by itself, I'm just going to get rid of this square by doing a square root to the other side. So I'm going to square both sides. And now I've got velocity final is equal to the square root of velocity initial squared plus 2 times a times d. And I'm also going to make it a little more user-friendly. So I'm just going to strip off the velocity final. I'm going to say velocity is equal to the square root of, and most of the times you see it written out like this, which is v naught. But I like to say v sub o, or I like to say velocity original, which is the same thing as saying velocity initial. But I'm just going to say that velocity is equal to the square root of velocity original squared, this time plus or minus 2 times a times d, because this is more than likely how you've seen this formula written out in your reconstruction materials and everything else. Now, if we're doing some kind of physics problem or something like that, you would just see it written out as velocity initial squared plus 2ad, but in most of your reconstruction stuff it's going to be plus or minus, and that just makes it a little bit easier for us to figure out if we need to add or subtract, with regards to the vehicle speeding up or slowing down, and we don't have to worry about as many designations and things like that as in a physics textbook. All right, so the question, how accurate is this going to be, or how close is this going to be to the minimum speed equation? We know that our minimum speed equation, which speed is equal to the square root of 30 times distance times drag factor, we know that this is derived from kinetic energy. All right, and we know that kinetic energy is the energy of motion. And what a lot of you may not realize is we can actually use this kinematic motion equation, and we can use that in one option to solve and derive that kinetic energy equation, which is kinetic energy is equal to half an object's mass times its velocity squared. We're not going to do that here, but we can actually use the work equation or the work energy theorem in conjunction with that kinematic motion equation and derive kinetic energy. If you want to see that, there's plenty of videos on YouTube that'll outline that for you. If not, just take my word for it that we can use that as one option to derive kinetic energy. So both of these formulas are going to probably give us very similar results. All right, so let's do our apples to apples comparison. We're going to say that we have a vehicle that skids in, and in this time we're going to say that we've got our Mustang, and we're just going to say that we've got a point to where that Mustang goes airborne at a speed of 27 miles per hour, or he goes airborne at a velocity of 39.58 feet per second. We're going to keep everything simple. We're going to say that he only travels a distance of 40 feet prior to going airborne, and we're going to say that the drag factor of the roadway is going to be a 0.78. All right, so now I have everything I need to solve this with velocity. Now, step one, I'm just going to write out my formula. Velocity is equal to the square root of the velocity original squared plus or minus 2 times a times d. Now you notice that I don't have an a variable written up here just yet, but if I want to do that, it's very simple. I just say that a is equal to my drag factor, or my acceleration factor, times gravity. So I'll say a is equal to 0.78 times 32.2, and that's going to give me an acceleration of 25.11 feet per second, or feet per second squared. So now I have everything I need to fill this in. So I'm going to say velocity is equal to 39.58 squared. Now, where people get hung up a little bit when using this formula is, do I add or I subtract? So what we need to do here is just listen to the car, what it's telling us, listen to the story that the car is telling us, and it's going to tell us whether we need to add or subtract. So the way I do this is, if he is skidding or he is slowing, his speed should be greater on this side of the problem than it is over here. All right, and I'm starting here, and I've got the car going in reverse because I'm backing him up to try to see what his speed is here at the start of the skid. So I'm working this vehicle in the backwards direction, and my arrow is actually pointing towards the plus. So I'm going to say plus 2 times 25.11 times our distance of 40 feet. So now we'll say that velocity is equal to 1566.57 plus 2 times 25.11 times 40 is going to be 2008.80. All right, so I add those two together, and I'm going to be at 75.37. Under the radical, I take the square root of that number, and I'm at a velocity of 59.78 feet per second, or a speed of 40.78 miles per hour at the start of that skid. So how does it compare to minimum speed? Now, one last thing I'm going to show you about the minimum speed formula is this is something that, an equation that some of you may not have a whole lot of experience using, because what we have looked at so far and what you had in your reconstruction training a lot of times is, to figure this out, you would say that the speed 1, or the kinetic energy equivalent speed, was equal to 30 times distance times drag factor, and you would do that with the 40 feet of skids, and then you would say that his speed combined was equal to the first kinetic energy equivalent speed plus the speed at airborne squared, and you would take the square root of that. So a couple of different steps, and it's fine to do that. It's just a little bit more work, but what I'm going to do here for this example is I'm going to kind of marry these equations. All right. And what I mean by that is I'm going to kind of combine these into one thing that's going to give me the best of both formulas. So this formula you may or may not have ever seen before, but it's pretty simple. It just says that speed is equal to the square root of speed original squared plus or minus 30 times distance times drag factor. All right, so this looks very similar to our velocity formula. We're just keeping everything in miles per hour as opposed to feet per second. And also you notice that I don't have to calculate an A value for this. I'm just going to be using the drag factor of the roadway or the acceleration factor of the vehicle, if it was speeding up. So I'm going to say speed is equal to 27 squared plus 30 times 40 feet times 0.78. So speed is equal to 27 squared is going to be 729 plus 30 times 40 times 0.78 is going to be 936. I add those two together and I come up with 1665 under the radical. I square that and I am at a speed of 40.08 miles per hour. So yes, we're off a little bit from velocity, but our whole numbers are the same. We're essentially getting the same answer. We're getting a speed using both of approximately 40 miles per hour at the start of the skid here. All right. And the reason this works out well is because now instead of dealing with the kinetic energy equivalent speed, if I was backing him up over multiple surfaces, I could say what the speed of that vehicle was at each segment, and I'm not getting a lot of confusion on having 2 or 3 kinetic energy equivalent speeds. So the way we can kind of look at this is we're basically just marrying these equations, because once I made this problem here, once I said 30 times 40 times 0.78, I was pretty much doing what was under the radical for the minimum speed equation. Because if I was going to figure out its kinetic energy equivalent speed, I would of course say speed 1 is equal to 30 times distance times drag factor. And I would say 30 times 40 times 0.78. Once I multiplied all those together, I was going to be at 936. All right, so I'm just kind of taking a step out. And if I wanted to figure it, the rest of the way out, it would be a kinetic energy equivalent speed of 30.59 miles per hour. And of course, we know that he wasn't going 30, so he couldn't have stopped because he went airborne at 27. But it's a little easier to do this equation here. I used to not like this equation a whole lot, but then once I started using it, I started to get the hang of it. It is a lot easier to do than just trying to do all those speed, kinetic energy equivalent speeds and then combine them together, because I really like the velocity formula because I could back up each section and know where the vehicle was at specific times. But now I can do the same thing, keeping everything in miles per hour. So it's just a user's choice. There's really no wrong way to do this, but the bigger picture is, one, we have more of a kinetic energy derived equation. On the left side of the screen here, we've got the kinematic motion equation, and they're both giving us pretty much the exact same answer. We're both at 40 miles per hour, and both of these formulas are going to have, sensitivities to the drag factor or the distance, about the same as well. So there's no real reason to go through here and look at how much the drag factor would affect the velocity formula, because it's going to be a similar outcome, similar in nature to that we've already covered, looking at the minimum speed equation and all that. So that's going to wrap up our 30DF versus 2AD episode. Hope you learned something new and got something out of it. If you did, be sure to hit like, leave us a comment, subscribe on our YouTube channel, share it with a friend. Anything like that is greatly appreciated. And also be sure to go to crashtrainingsolutions.com/podcast. crashtrainingsolutions.com/podcast and get the visuals for this episode that you'll have with you that you can refer back to later if you'd like, and all that good stuff. So until next time, I'll see you guys on the next one.